Now we want to consider mismatched typicality. So we consider the event that we have a discrete memberless source concerning some probability distribution Px, which outputs a sequence x tilde n, which is typical in the typical set concerning to another probability distribution Px tilde, where Px tilde could be different than Px. It could be, of course, that we estimate the discrete memberless source wrongly and we look at the sequence. What we want to know is what happens if we have such mismatch. So we refer to this situation as mismatched typicality. First, we look at an easy case. So we suppose that we have a letter A such that the probability concerning X is 0, but concerning Px tilde is greater than 0. We know already that we showed before that if epsilon is smaller than 1, then x tilde of n is in the typical set of Px tilde, implies that that na of xn is bigger than 0. So the letter have to appear. But if the letter have probability 0 concerning Px, we know it's not in the set of typical sets of Px. So it's not in that typical set. So we have that the probability that xn is in the typical set of Px tilde is equal 0 for epsilon smaller than 1. So this is not so interesting case. So mostly we will consider a probability distribution where we don't have the situation, or a little bit more generally, we look now at the situation where Px tilde is covered by Px. That means everywhere where Px tilde is non-zero, Px is also non-zero. So, and this, what does the theorem say now? We suppose that epsilon is greater than 0 and xn is emitted by the discrete memberless source Px, and we make the assumption that Px tilde is covered by Px. Then we can estimate the probability that xn is in the typical sets of Px tilde by 2 to the minus n, and then the relative entropy between Px tilde and Px. And this term goes to 0 as you see, and this term goes to 0 as you see, and this term goes to 0 as you see. So we can really estimate this probability by 2 to the minus n times the relative entropy of Px tilde and Px. We want to prove this now. Therefore, I open again a whiteboard for you. So let's see. So first we share a look at the probability concerning x of x tilde of n. This, of course, so for the proof, we just assume that all probabilities are positive. So this is equal to the product over all A in x tilde and B Px of A, and then we do it like we did before. We count just the number of appearance of A in x tilde of n. That's just the probability of a sequence concerning Px, that this sequence is produced by Px. This we know by the definition of typicality. We know that smaller equal to the product, and now we can replace this NA of x tilde of n by n times px tilde of a times 1 minus epsilon, because x tilde is typical concerning px tilde, and this is just the definition. This we can write now by 2 to the logarithm, and then we write the same product over all a, and we have here px of a to the n px tilde of a of 1 minus epsilon. That's only we write it longer here. And now we have here the logarithm of a product, and of course it we can write as a sum. So this is equal to 2 to the sum of, and if we have the logarithm, then this goes to the front over all a we have here, then we have n 1 minus epsilon px tilde of a, and then the logarithm of px of a. So we just write the product here as a sum because we take the logarithm here, and then we, for all logarithms, we have this part goes to the front here, and we get this here. So now we want to use this to calculate the probability. So therefore we delete this here, just have it in mind what we have there. Now what we really want to calculate, to estimate, is the probability of the event that xn is in the typical sets, it's a t here, and epsilon of px concerning px tilde. This, of course, we can write as the sum over all x tilde n in p n epsilon of p x tilde p x n of x tilde of n. Now we know we are just estimate this part here. We estimate this probability here by the sums here. So we can write this or estimate this as the sum over all x tilde to the n. And then here what we did before, we have here 2 to the sum of n times 1 minus epsilon, and we have here p x tilde of a. So we sum here over all a, of course, and the logarithm of px of a. But this we can write as, now we have all sums are, all elements of the sum are the same. So we have in total here, like we did it every time, we have here, we have exactly t, the cardinality of the typical set of px x tilde here, times, and now we just write this here, the sum over all a n 1 minus epsilon px tilde of a log px of a. Now this we can estimate now, because we can estimate the cardinality here. We know how to estimate it. We can estimate this by 2 to the n of 1 plus epsilon and h of px tilde here. And here we have again 2, and the same here, the sum over all a, n times 1 minus epsilon px tilde of a log px of a. Now we know that this hx of tilde we can replace, so this is equal just to minus the sum of px tilde of a log px tilde of a. That's just the definition of the entropy of x. If you now put everything together and sum this up, then you see immediately that we get that we can estimate this by 2 to the minus n, and then we have the relative entropy between px tilde and px plus epsilon and some r. So exactly that is the proof. And the reason is really that we have the entropy here, and we are in our estimation we have px tilde of a times log px of a. That's exactly what you have in the logarithm, and all things which is multiplied by 1. If you put this together, you get exactly the relative entropy between px tilde and px, and all things which you multiply by epsilon, we write it with r, and that's the remaining term. And in the same way, you can estimate it in the other direction.